Okay, so let's go over some of these reactions from yesterday. So this is like, especially for those of you taking the AP chemistry test itself, this is kind of like general knowledge of science or chemistry, and also specifically a lot of these are redox reactions. So speaking of redox reactions, you've got a quiz coming up on Thursday over redox reactions, half reactions, what's reduced, what's oxidized, what's a reducing agent, what's an oxidizing agent, that type of thing. So let's jump straight into number 6, okay? So you got a solution of sodium iodide and an acidified solution of sodium permanganate are mixed. All right, so there's 2 things that you need to know about this. What you need to worry about and what you don't need to worry about in terms of writing the net ionic equation. So you have a solution of sodium iodide. So literally, if you ask me to say, hey, Burkham, I need to mix up a solution of sodium iodide, I would go to the shelf, sodium iodide, oddly enough, it's a white crystal, looks like salt, and that's going to be NaI. Okay? So why, if you look in the chemical storeroom, there's a lot of stuff, and it's organized alphabetically. There's a lot of potassiums, and there's a lot of sodiums. Okay, that's by far and away like the vast majority of chemicals. Sodium acetate, sodium iodide, whatever. Okay, potassium iodide, potassium hydroxide. Why do you think so many of those things are bound to sodium and potassium? Number 1, they're soluble. Okay. Number 2, they're cheap. They're abundant. Okay. We don't have a budget order chemicals that cost like $10,000 for a bottle. Okay. And the reason it's sodium and potassium is because those bond very easily with a bunch of anions. Okay. So the vast majority of the stuff that we have are ionic compounds, and the vast majority are sodium and potassium because that's what's most abundant. So here's what's important. I would mix this stuff up in water. Physically, this is where I mix this up. Okay, soluble or insoluble? All group 1s are soluble. So here's what's important. This is existing as sodium ions and iodide ions. Not elemental iodine, okay? Ions of iodine, which means that these have gained an extra chihuahua, the sodium has lost a chihuahua. Okay, cool. Now, we're going to add sodium permanganate. You all have dealt with sodium permanganate with that dark purple stuff, right? So that's Na, and then you have MnO4 minus. This is soluble. And then it's an acidified solution. So what would we add to make it an acidified solution? Yeah, we'd add some type of strong acid, okay? Maybe sulfuric acid, nitric acid, something like that. We're just going to dump in a bunch of hydronium ions into this, okay? So, do you think you're going to worry about the sodium? No, okay? Right away, is the sodium there? Am I going to care about it? No, okay? Not going to happen. So part of this is also eliminating what type of reaction it's not going to be, right? So this is, why would this not be a single displacement reaction? Yeah, well, what do you have to have a single displacement reaction?
Different cations.
Different things.
Yeah, we got the same thing. You ain't wrong.
3rd semester of chemistry at Mays High School, I end up with different things. Brilliant. Okay. Now, really, that was so sarcastic. So let's say, you look at, like, say, for example, number 2 up above. Okay? A solid piece of zinc is placed in a solution of copper 2 nitrate. You think that would be a single displacement reaction?
Yeah.
Why?
Because
And so help me God, if you say you have different things, I'm going to
you got like one cation, and then you got like a whole compound.
Bro, you have one thing and another thing.
Yeah, that's what I'm trying to say, but he doesn't like the word thing.
I'm trying to.
Okay, you have one entity. You have another entity that's made of 2 sets.
Okay, this side of the room doesn't get to talk anymore. Let's hear from the right side or the middle. Rachel, save me, please.
Wait.
I don't care about the
Hey, Big Mike's here saying.
Good, Mike.
Can you say the question again?
I feel like Nathan was
No,
talking.
because if you say the question
Okay.
again, I got it.
What is our criteria to have a single displacement reaction? Big Mike.
The anion. The cation. The cation has to go to the other thing. The other reactant. The other reactant. The other reactant.
One of the reactants has to be in its elemental form.
Oh, somebody said it.
One of the reactants has to be in its elemental form.
One of the reactants has to be in its elemental form.
That's what Mike will say.
Which is not a thing.
Yeah, that's what.
Okay? If you look at number 2, right? Or let's say, for example, I'm going to do this. Here I have a solid piece of magnesium, and I'm going to add to that a little bit of copper nitrate. Okay? So I'm going to do this. Okay? Let it sit there for a little bit. So first off, what we need to figure out is, number 1, that this is going to be a single displacement reaction. Because you have 2 things. What are the 2 things that you have? An element and
A compound.
an ionic compound. The ionic compound almost always is an aqueous environment. Okay? So number 2, you have zinc. Very similar to magnesium. And you're going to put that on number 2 in the presence of copper 2 nitrate, which is what I happen to have right here. Right? So let's jump back to this. You have zinc and copper 2 nitrate. So this is why we're studying redox reactions. If you play the over-under game, where's zinc in relation to copper? On the redox chart that you're going to have on the quiz on Thursday. You have to be able to use the chart. Where are zinc and copper relative to each other? Copper is, zinc is below. So if you do the over-under game, now you also have to remember, this is copper ions and elemental zinc. So if this reaction happens, the Cu2 plus is going to gain 2 electrons, and it's going to turn into elemental copper. And if you could look at this, okay, you're seeing this solution turn an orangish red, because what's happening is that you're having a single displacement reaction taking place between the magnesium and the copper. So in this situation, it's the zinc, it's the same idea. So you have the elemental form in the solid form, the zinc, the copper, whatever that is. Then around here, you have Cu2 plus ions. They're floating around. So basically, this is, again, it's a battle for the electrons. Who is going to win? Who wants the electrons more? Does the copper ions want it more, or does the zinc want to hold on to its own? So there's 2 ways you can do this. You can do the over-under game, okay? But keep in mind, this is so vital, because there's a huge difference between having elemental copper like this, okay, which is the shiny copper-looking metal, oddly enough, because it's copper, and copper ions, which are a blue solution. Both copper, same number of protons, same number of neutrons. The difference is 2 chihuahuas. You take away 2 chihuahuas, it turns into a blue solution. You have all of the chihuahuas, it's a metal that conducts electricity. And the only difference is 2 chihuahuas. Okay? So, same thing is going to be true of zinc. I'm going to put this in here. So, to have a single displacement reaction, sometimes it's referred to as a redox reaction. You have to have the elemental form of a substance and an ion. Okay? And then you have to swap out chihuahuas. So in this situation, is the copper capable of taking chihuahuas from the zinc? because it's above. If you want to do the math, if you take the Cu2 plus, what's the standard reduction potential for copper? 0.34?
Yeah.
Okay? And that's going to stay as it's written. That's 0.34. But the zinc is going to get reversed. So the zinc, because we study redox reactions, not re-re, not ox-ox. So if the copper is going to get reduced, the zinc has to get oxidized. So which means that you have to take the reaction as it is written on the page and flip it. But when you flip the reaction, what do you do with the sign of the E naught value? Flip it as well. Okay? So you flip the sign of the E naught value. What's the E naught value for zinc?
0.76.
So that becomes, once you flip it, it becomes positive 0.76, and you get 1.10 volts. That's a positive number. As long as that number is spontaneous, you're going to have a reaction. Now, if I switch it, if I take a piece of copper, okay, take a piece of copper, and then I take some magnesium nitrate and put that on there, now what's going to happen? So I have elemental copper and magnesium ions. What's going to happen?
Nothing.
Absolutely nothing is going to happen. Why not?
The energy is negative.
Well, the standard reduction potential is negative. So here, if you play the over-under game, and this is what I want you to see is the difference. Okay? So with this one, where did it go? And this is what I want you to see what's kind of cool about chemistry. The only difference here are where the chihuahuas are. Chemistry is just the rearrangement of chihuahuas. If I take copper ions and put that with magnesium, I get a reaction. Copper takes away the electron. It's a blue solution and a silver piece of magnesium. I take magnesium nitrate. Only difference is that now magnesium nitrate is a clear solution. It looks like water. If I have elemental magnesium, it's silver. If I take away those two electrons, it now becomes a solution that looks like water. I put that on copper. Elemental copper is this copper-looking color. I take away two electrons, it's a blue solution. And the only difference is where the chihuahua is.
Is it blue because it's sad?
If that was the case, I would blend in with my shirt. So, no, just based upon the answers to what criteria is there for a single displacement
I
reaction.
got it right.
Eventually.
I was saying elemental form for like 5 minutes.
Oh, you were not. That was a bold face.
Because I was selling it. I'm non-verbal.
I'm not. Okay.
Yeah.
So back to our story of number 6. Okay? Way back to our story. So you have iodine, right? And you have the MnO4. That's the only thing I'm going to worry about. And I'm going to have some hydronium ions because of the fact that it's an acidified solution. Okay? I don't know where the hydronium ions are. We'll worry about that later. So this is what you have to be able to do for this quiz on Thursday. So you got to do 2 half reactions. Which one do you want to do first? The oxidation or the reduction? Reduction. Okay. Now, but you have to figure out what the products are out of this. Okay? So you have MnO4. What's the oxidation state of manganese at that point? +7. Okay, that's a skill that you have to have. You need to be able to look at this and go, oh, oxygen is 2 minus. 4 times 2 gets me -8. The whole thing has to add up to -1. That has to be +7. Okay, if you cannot do that, you are dead in the water. Okay, like you are trying to swim with weights tied around your waist. It is not going to happen. Now, this is going to end up at Mn2+. Okay, this is what you all did on the lab. Okay, you all did this reaction. We're going to have to go all the way to Mn2+. So, you have 7+ going to 2+. Gaining chihuahuas, losing chihuahuas. gaining, because you have a deficiency of 7 chihuahuas. It's probably not going to lose any more than that. Okay? It's probably going to gain this. So how many did it gain? 5 electrons. So there's 5 electrons involved. Now, those electrons have to come from somewhere. So let's look at the possibilities of where it could possibly come from. Okay? You have Na plus ions. Okay? How many chihuahuas does the sodium ion have?
I mean, what?
How many chihuahuas does the sodium ion have? Big Mike.
10.
Yes, thank God. Why?
Because it's 11, but it's positive, so it lost 1.
Beautiful. Okay? It would normally have 11. If it was elemental sodium, it would have 11. Lost 1, we're down to 10. Why did it only lose 1 chihuahua?
Neon.
Because it's plus 1.
It has fun.
It wants to be like,
Neon.
which is the noble gas in the
10.
in the row up above, right? Okay, so it wants to be like neon. So to do that, it's going to lose an electron. Okay. If you really want to get fancy, that's 1s2, 2s2, 2p6, 3s1. It has 1 chihuahua way out on the outer border region. Okay. Basically, anything comes along and says, "Hey, spare a chihuahua," sodium goes, "Deuces, take that thing." It's annoying. Okay. It certainly doesn't want to gain 7 more. When I was in Africa teaching this, I used goats. Okay. I said, "Hey, you have 1 goat. Is it easier to lose 1 goat or gain 7? And the kids go, "Ah, teacher, it's much easier to lose 1 goat." I said, "Boom, there you go." So in Africa, I explained this with goats. I use chihuahuas here. So that's gone. So here's the question. Could, since manganese is leading chihuahuas, could it take away an electron and make that Na2 plus and take an electron away from it?
Unlikely.
Could.
But it's
Unlikely. Why?
Because why would I want to go farther? You're just supposed to be in its own form. Why would I go farther past? Like, why would I want to go more? You know. My brother, what?
No.
If it takes another electron and gets closer to its elemental form.
That's what. Yeah.
It wants to.
Yeah. Why would I want to go farther?
No. So look at the way he's looking at you. Stop.
Okay, if it's Mn plus 7 and it gains an electron, then it's Mn plus 6, which is closer to Mn.
I'm talking about the sodium. You're right, but I'm talking about the
It
sodium.
has a full like that. I heard Nathan say Mn.
What?
I think you might have said amen.
In
Big Mike.
Not apple.
Alright, so Na plus 2. Alright, that's like chlorine. Why would you want to be chlorine when you could be neon? Na plus, that's neon. And then,
Why would you want to be neon as opposed to chlorine?
well, because neon's more stable. You know?
Why?
Because it has a full valence electron shell.
Oh, it has 2 electrons and an 8. Okay? Law of octets, right? So if it took away an electron, if it did, what's sodium going to try and do if it takes away 2 electrons, if it loses another electron? This is going to try and take that electron back and become more like the noble gas of neon. Okay? So this, not going to happen. Okay? Not going to happen. Now, would it be possible, speaking of sodium, for sodium to gain an electron and turn into elemental sodium?
Yeah.
Could that happen? Could. Not likely. Yesterday, I dropped a piece of sodium in water. What did it do? Reacted violently and produced sodium hydroxide. So even if you made sodium, what would it do?
It would go boom.
It would just react with the water and go back to sodium ions and generate hydroxide. Okay? So sodium is stable. Sodium's going, I've lost my electron, I'm stable, get away from me. Okay? I'm not going to give away electrons, I'm not going to take in electrons, I'm not going to go back to being elemental sodium, I'm not going to lose another electron, become like fluorine. I'm good. Sodium is basically saying, everybody just leave me alone. I'm going to watch the reaction take place. You all sort this out. I'm staying out of it. Okay? Now, you have iodine, right? So iodine is relatively big. If you look at the periodic table, well, iodine's one of the halogens, and it's farther down. So it does have, it's gained an electron. Okay? So why, in contrast, why did iodine gain an electron? And so if it gains an electron, what does it look like?
Xenon.
Huh?
It looks like xenon.
Yeah. Is it xenon? No. Okay. If you make me look like Snoop Dogg, I ain't Snoop Dogg. Thank God for that. Okay. Well, as far as you know. Saturday nights when I'm spinning up the records, you know, that's a whole other story. But
He's wearing blue too.
little cheap. So iodine does have that extra valence electron, but it's capable of giving it up. So here's the story. So when you look at this, okay, you can find iodine on here, right? Notice that that's fairly far down on this reduction chart. That's like 0.53, right? So iodine does want to take in electrons, don't get me wrong, but it's one of those that we could fairly easily reverse it and make it go back to elemental iodine. So here's what's going to happen. You're going to have two products, elemental iodine and Mn2+. Okay, those are going to be your two products. Now, does anybody out of your random knowledge of chemistry, anybody know what elemental iodine looks like?
Is it white?
No.
It's black.
No.
It's brown.
It's like dark brown.
It's reddish brown.
It's reddish brown.
Okay? It's reddish brown, and it's like a liquid / solid depending upon the temperature. Okay?
It's used in hospitals to get rid of bacteria.
Exactly. Okay? Mainly because of the fact that it wants to take in electrons and turn it into iodine 1-. Okay? And it takes those electrons from the bacteria. That's why it's used. Okay. So, if this reaction happens, and we're going to do reactions with this, you will see a layer of brown, like a precipitate form, and that's elemental iodine. So, here's your two reactions. You have iodide turning into iodine, and you have MnO4 turning into Mn2+. Okay? So, what's happening with the iodide? Oxidized, reduced.
Oxidized.
Why? Lost an electron. Now, am I going to do this? Is that right?
No.
Why should there be two? That's the most common mistake that's made. Everybody sees this, you go, oh, that's 1-, I'll just put one electron over there, we're balanced and we're cool. Okay? But are you balanced?
No.
No, you have two iodines. What do you need? Two over there, and then you're going to need 2 electrons there. Right? Most common mistake that's made. You have to do that with the iodine. MnO4 is going into Mn2+. 7+ is turning into 2+. How many electrons do I need? Which side, left or right? Product or reactant side?
Reactant.
Plus 5 electrons. Okay? Got that. I have 4 oxygens. What am I going to do?
Add 4 H2O to the other side.
I'm going to need 4 waters over here. Then what?
H plus.
And why? And this is why it needs to be done in an acidic environment, because you need those hydronium ions. Okay, that's the role of the acid in this reaction. Okay, so now what?
Let's do the charges. I'd multiply.
Multiply what by what?
Top one by 5 and the bottom one by 2.
This by 5. This by 2. Why?
To get the electrons out.
Because electrons lost have to equal the electrons gained. Okay? So, that's going to get me to 10 electrons. That's going to get me to 10 electrons. Those are going to cancel out. Now, how can you make sure that your half reactions are right?
Charge and the quantity.
Charge and quantity. If you take the time to check that, and if they're right, at least you have a fighting chance. If they don't balance on charge or number of particles, I promise you, no matter how much you wish that it was right, it's not going to be. Okay? I promise you, if they don't balance on charge and number of particles, and usually isn't the number of particles, usually it's charge. Okay? I promise you, you are not going to win. You are not going to win at all. Okay, so then we're going to have like 10I minus. We're going to have, we'll multiply all of that by 2, so we're going to have 16 hydroniums. We're going to have 2 MnO4 minus. We're going to have 5 I2s. We're going to have 2 Mn2 plus. And we're going to have 8 waters. So when you get done adding the two half reactions together, again, what should this balance on? Charge, number, particles. If you go through and you go, okay, hey, I got 10 negative charges here. I got 16 positive charges there. That gives me 6 plus. I got 2 negative charges there, so I'm at 6 plus minus 4. That gets me 2 plus 2. I come over here, then I've got 2 charges. No, I screwed that up on the map. I did. So I've got 2, I got plus 4 over here. If you go through all of that math, you get plus 4 on that side. Boom, you're balanced. If it doesn't balance, you're screwed. Okay? All right. That was one of the more difficult ones. But that is something you need to be able to do without thought. Number 5 is 5 a redox reaction. Is 5 a single displacement reaction?
Yeah.
Yes. Because it's chlorine gas.
Elemental.
Okay. So you got. So here's what would happen if you were going to mix this up. I won't demonstrate this for you because chlorine gas is highly poisonous. That's why I'm not going to do this. So you'd have a container of chlorine gas, right? And you'd hook that up to a hose, and you would bubble that through this solution. So you've got sodium bromide, sodium ions, bromide ions, and then you're going to add chlorine gas to it. Okay? So if this is going to happen, right, do the over-under game. You've got chlorine gas up here, 1.36. If you come down here, you have bromine, which is below that, which is 1.07. So the cool thing about the halogens is that they are their own reactivity series. The most reactive halogen is at the top, and that's fluorine. So literally, the halogens are their own reactivity series. And the reason that happens, and here's a very short lecture which we'll get into more later. Do the halogens react by gaining electrons or losing electrons? Gaining electrons. How many do they gain? 1, right? Because they want to be like noble gas. So the reason that fluorine is the most reactive, if you go up here and look, fluorine way up there at the top, the reason that that's most reactive is that which valent shell is fluorine filling? First, second, third? Second, because it's the second row down. So fluorine is filling up that energy level very, very close to the nucleus. So and the closer it is, the stronger that attractive force is and that ability to pull in electrons. So for those of you that are in AP physics or have taken AP physics, that is the result of F equals K Q1 Q2 over distance squared. This just tells you the amount of electric force. So this is the charge and this is the distance. So fluorine has a relatively small distance. That creates a big force in terms of being able to draw in those electrons. Chlorine has a bigger shell because it's filling out that third one. It's a bigger distance, that attractive force is less. So here's what you would see. If you did this, the chlorine more reactive than the bromine. So it's its own reactivity series. So basically what's going to happen is that you're going to get Br2 and chloride ions. Okay? Now, bromine is kind of like iodine. It's like a brownish red. So don't worry about the sodiums, not part of the story. So you have Br minus plus Cl2 turning into Br2 plus Cl minus. Balanced?
No.
Horribly wrong. What do you need to balance it?
2 and a 2.
2 and
1, 1, 2.
2. Okay, so there's that reaction. Number 10, lead-2 nitrate and sodium sulfide are mixed. What type of reaction is that?
Double replacement.
Yes.
Which one?
Okay, no. Mr. A thing and a thing, no.
4 things.
He's bad. It's not how about you start, it's how you finish.
Yeah, that's right.
Yeah.
Not just start, so you finish.
Yeah.
That's what life's all about, baby.
Come on.
Yeah, that's what General Custom said too. How'd that work out for you? Okay, so, yeah, that didn't get it well. So, the whole key to this on number 10 is that it's a solution of lead-2 nitrate and sodium sulfide. So, how are these things going to exist? Pb2 plus nitrates. Sodium. Now, what's the formula for sulfide?
2.
SO3.
Iodines 2.
It's just S. S.
SO2.
Sulfur is 2 minus, but why is it 2 minus?
Because it's 2 this way.
Because it's 2 this way.
It's 2 of them.
Oh, I
Because it
It
wants
wants to
to
gain
it
2
wants
electrons.
to-
Why?
To
It
fill
has
the outer
6.
valence.
How many valence
4.
electrons does it have?
6.
Because it's in the same column as oxygen.
Oxygen.
Yeah.
Okay. Thor, stop. So it has 6 valence electrons. It wants to get to 8. There you go. So here are your 2 possible products: lead sulfide and sodium nitrate. Which one will form the precipitate? Lead sulfide. Sodium nitrate will never make a precipitate because all nitrates are soluble and all group 1s are soluble. So this is going to be Pb2 plus S2 minus turning into, would you expect the KSP value for lead sulfide to be a really big number or a really small number? Small number. That's what allows it to make a precipitate. You have small KSP values. Okay. Good? Okay. All right. So here we go. So let me hand out the next thing that you need. So stop the other camera, please.